Every modern convenience relies on an invisible technological foundation. Artificial intelligence, systems that process massive data to simulate human learning, from everyday smartphones, EVs or electric vehicles, and advanced military hardware, all share a single critical dependency. They cannot function without microchips. This chart shows the widening gap between global semiconductor demand and the available workforce, projecting out to 2030. Within the next few years, the world will be short roughly 1 million trained semiconductor workers. Without the engineers to design, test, and manufacture these components, production lines slow down. A deficit in human capital at this scale threatens to bottleneck the entire global tech economy, delaying product cycles and inflating costs across every hardware-dependent sector. For decades, Vietnam operated primarily as a basic electronics assembly hub. Now, the country is executing an aggressive strategic pivot, targeting the high-value core of the industry, mastering the technology behind the silicon wafer itself. Massive foreign capital is pouring in to support this shift. Industry giants like Intel, Amkor, and Synopsys are heavily expanding their research, testing, and manufacturing footprints within the country. This sudden influx of investment has created a massive local vacuum. Right now, Vietnam is only producing enough high-tech talent to meet 20% of the industry's demand. To fix this, the government issued Resolution 57 NQ/TW. This is the state's highest-level strategic roadmap, and it explicitly prioritizes science, technology, and digital transformation above all other economic sectors. The mandate carries a specific, aggressive quota. Vietnam must train 50,000 new semiconductor engineers by the year 2030. 50,000 engineers provides the personnel needed to run incoming research centers and fabrication plants. Reaching this specific workforce target is a prerequisite for moving the economy past simple electronics assembly into higher-value chip design and production. This diagram illustrates what is known as the development triangle. It is a highly specific ecosystem that directly connects the state's strategic mandates, the technical needs of private enterprise, and the training programs of universities. Because enterprises directly communicate their hardware and software requirements, universities are discarding traditional theory-heavy curriculums. They are restructuring their entire academic approach to prioritize practical, hands-on engineering. This shift has triggered extreme academic competition. Cutoff scores for these specialized tech majors have soared, with some programs requiring 29.37 points out of 30 just for admission. Once admitted, students experience a massive operational shift. Universities are investing millions in cleanroom labs and OSAT training. OSAT stands for Outsourced Semiconductor Assembly and Test, the precise stage where raw silicon pieces are packaged into functional chips. Institutions like Howey are upgrading to meet EBIT standards, the Accreditation Board for Engineering and Technology, a strict international baseline, while schools like FPP, FINICA, and HUST are rapidly building out their simulation and design faculties. Because the curriculum is dictated by the companies hiring the students, graduates are immediately deployable. They immediately enter the workforce without requiring months of traditional corporate retraining, solving the industry's single biggest logistical friction point. Building advanced engineering curriculums from scratch takes decades. Vietnam is bypassing this timeline entirely by importing established foreign expertise to train its domestic workforce. FPT, for example, finalized strategic partnerships with Indian educational powerhouses Jet King and Cranes Varsity. This alliance is designed to rapidly train a cohort of 1,000 students using pre-vetted international syllabi. The focus areas are strictly high-value: artificial intelligence, IC design, the complex architecture of integrated circuits, and the engineering of UAVs, or unmanned aerial vehicles. Simultaneously, a direct export pipeline is taking shape. Vietnamese students are being sent abroad to fill specific regional workforce deficits, such as the estimated shortage of 1,000 engineers per year in Kyushu, Japan's major chip-making hub. Importing advanced curriculums accelerates domestic training, while exporting talent builds a network of global experience. These strategic educational partnerships create a knowledge transfer mechanism that integrates Vietnam's workforce directly into the global semiconductor supply chain. Surviving these rigorous tech programs requires years of intense study. The core question for any student is the actual financial return on that investment. Entry-level salaries for fresh graduates range from 10 to 20 million dong per month. With 3 to 5 years of experience, compensation jumps to between 25 and 50 million. For high-level experts, the domestic ceiling pushes past 70 million, while international postings range from $80,000 to $150,000. Compensation structures at this scale bypass the traditional corporate ladder entirely. For the average Vietnamese engineering student, mastering this specific skill set alters their trajectory of socioeconomic mobility. Economists frequently note that data and the semiconductors that process it have become the oil of the 21st century. Historically, career paths relied on incremental growth in established industries. Today, a highly specific window of opportunity exists for those who can build the hardware the rest of the world relies on. By entering this field, these engineers secure their own careers while building the technical infrastructure required for the nation's digital transition.